Assalamu alaikum wa rahmatullahi wa barakatuh. Today we are talking about the chapter in KNX Certifying Basic Course, the chapter called RF. RF stands for radio frequency, and it's talking about mostly how to connect the wire system. For the past chapters, we're talking about the wire system using a TP or even a backbone from an IP network. Then we are talking now about how to connect this in the wireless world using radio frequency protocols under the RF, under KNX. First, we're talking about the attenuation. The RF frequency KNX is using is a megahertz frequency, which is 868. By the way, 868 megahertz. This is, by the way, the same frequency that the Z wave in Europe and Middle East is using. Okay, and as any wireless protocol or wireless frequency, okay, it will have attenuation when it's meeting obstacles, like the signal here is that strong, but when I'm going after, let's say, 30 meters, the strength of the signal is going down. And then if I'm passing via a wall, it's going down by a direction, by a degree, okay? One thing worth mentioning here that most of the time when we are talking about wireless, what we see in the papers mentioning about the distance the wireless is covering is called a free field range. So when books or manuals are saying, let's say that the RF covers 100 meter, it is what we call free field range or an open area. Okay, and this most of the time is a theoretical range. So it's not covering 100 meter because in real life I have walls, I have gypsum boards, I have grass, I have directions, I have other obstacles that affect the signal, sometimes in tweaking the signal and make its strength lower and less. Okay, most of the time also that devices of the RF are powered by battery because there is no power in here, so I cannot connect them using KNX cable, so they are powered by battery as well. Okay, let's talk about attenuation. Attenuation affects the signal in a bad way. So before the signal passes the obstacle like a wall, the signal strength is high, and then it might be lower after that. The factors that affect the attenuation is the type of the obstacle. So is it wall, is it concrete, is it glass, is it metal, and the thickness of it. So let's say a concrete with a thickness of 4 millimeter will affect the signal by, let's say, attenuation of 20 or 30%. But if the thickness of the wall is, let's say, 1 centimeter, meaning 10 millimeters, then the signal will be more weakened after passing that. Also the direction, so the angle of the signal. So let's see here, as you can see here, this is, let's say, the source. This is a device with the antenna, and it's sending telegrams, wireless telegrams, different direction. So as you can see here, once the telegrams pass from this one, okay, the signal dropped apparently higher than it was dropped here. So here it was dropped a bit, but here dropped more. Why? Because this is thicker than this one. So as the wall is thicker, then the signal will be weakened. Also the angle of penetration. So here the angle of penetration was vertical, perpendicular. So you can see that it's not affected very much. But here it was with an angle, so it was affected more. So here the number of arrows represents the signal strength, by the way. Okay, so the first thing we need to know that there is an attenuation. So in my design, I need to consider this. We know from the course of the Z waves that we are teaching as well, that it depends on the obstacle and the type of obstacle. And in the Z wave course, we also have charts saying how much attenuation or signal drop depending on the obstacle I have. Also, there is something called shadows, and shadows are caused by metal. So metal obstacles are the worst enemy for the RF signal because it distracts the signals. Okay, so it might even cause that of dead areas. So we always recommend that avoid putting your, let's say, devices within a metal box. And like in Z-Wave as example, don't put the flash mount devices in a metal box. Try to get a plastic box if you can, okay? Because signal will be dead in here. As you can see here, it was distracted by this. It did not pass, but so here I have a dead added area. So I need to plan here to put another device repeater or something, maybe to take from here to cover this area again. So in my design, I have to consider something like that. Okay. Also, the reflection, that sometimes the signal is reflected from the obstacles. The reflection might be a positive reflection or a negative reflection. Positive reflection meaning that I add a peak to a peak, so there is strength in the signal, or I'm adding a peak to a bottom, so I'm canceling the signal, because this is a negative effect and this is a positive effect. So this is something also I should know and I should consider in my installation as well. The modulation, meaning how should I know that this is a 1 or a 0? Because at the end, I'm getting a signal and I need to interpret the signal to a 1 or a 0, then to transmit it, to transfer it or to change it to binary signal. So there are mostly two ways of modulation: amplitude shift keying and frequency shift keying. Okay, amplitude shift keying meaning that I check the power of the signal, the voltage of the signal. If it is high, let's say this amount, then it's 1 and this is 0, or vice versa. This is amplitude shift keying. Or frequency shift keying, meaning I check how many signals, what's the frequency in the signal itself. So if I have here high frequency, this can be a 0. Low frequency, meaning a 1. Okay? So it's either an amplitude shift keying or a frequency shift keying. The KNX RF is using frequency shift keying, and sometimes it's a question coming in the exam. So what kind of modulation I'm using in the KNX RF? I'm using a frequency shift keying. Moving on, propagation of radio waves. He wants here to tell you that the signal of the waves from the device is not the same in all directions. Okay, so here it's mostly more strength, here less strength, and here is more strength. So we know from also KNX from Z-Wave courses that the horizontal part is mostly stronger than the vertical part. From Z-Wave, we know that it's almost 30%. So the vertical on the antenna is 30% less on the horizontal part. And this you have to consider, because if you are covering a large area, then the area that you can cover horizontally is more than what you can cover vertically. Then in the vertical area, you need to put more repeaters maybe as you need. The transmission and the receiver is like that. So you have here the signal, it's a binary signal coming from the KNX, then it's going to the modulator and transmitter, and then it's being sent as waves using the frequency shift modulation that we talked about, and then being received from the other device, and then transmitted as or translated as binary again. It's very simple, and this is here a transmitter and a receiver. One thing appeared when they were using the RF in general, that because RF it can be used by other devices as well, then you might have some circumstances where there is jamming on one channel. So if you are using one channel, one frequency, and that's it, then maybe you have some kind of jamming from or disruption from other systems in the area itself, maybe from other DF devices, maybe from other RF devices, something like that. This is why they came with something they called multi-channel, meaning that I have a central channel and I'm using this frequency and some channels around this frequency, and I'm using this to make sure that the transmission is more reliable and more faster. So I'm not just stuck with one channel, but with more channels. Imagine it like you are going in a straight way, a highway, and then you have only one lane. So this lane, if this lane is stuck, then you are stuck, but most of the time you have more than one lane. So now you can go for more than one lane. And even like highways, sometimes you find that the right side is dedicated for the cars that are going in slow speed, but the left side is dedicated for cars going with fast speed. They have the same here, by the way. So they have fast channels for devices that need fast feedback and fast operation. They have slow channels for devices that doesn't need fast operation. So they say here, when I say RF ready, meaning single channel, by the way. Okay, so I have devices which are RF ready, this single channel, or I have the multi-channel, which can be RF fast or RF slow. So if I have main powered actuator like relay switches, I am mostly using transmitting and receiving via the RF ready or fast channels. So the actuators I'm most using for on the fast channels, like the relay switches. If I have battery powered actuators, then I can use the slow channels. If I have battery powered systems, then I can use the KNX ready or the fast channels. Okay, main power controllers like gateway and stuff like that, then I can use all the channels. So most of the time you have the question asking here, if you have a relay switch, which channels you are using, then mostly you are using the fast channels. If you have, let's say, HVAC controller, like for AC or for heaters, then you can use the slow channels. And why you are using fast and slow channels or multi-channel in general, to make sure that the signal goes there and there is more reliability in using fast, in using different channels, okay? This is not a really relevant, but it wants to show you that these are the ranges for the channels. So here a fast channel, then here a fast channel, and there are some other slow channels in here in this frequency. So around the frequency of 868, then you have the slow channels and fast channels as well. Now talking about the telegram is the piece of information that KNX is, let's say, using. So whenever I'm sending a chunk of data, I'm sending a telegram or more than one telegram. Okay, this is what we call it in KNX, a telegram. So it's like the chunk of data that's sent on the cable or even on the RF itself on the waves. A telegram in KNX RF can be analyzed like that. So there is a sync port, then a data block port, checksum to make sure that the signal is correct, then another data block, then a checksum, then a data block, then a checksum, and the sync. The sync apparently making sure that this is the start and this is the end of the telegram. And then you have a checksum in each telegram to make sure that the telegram is delivered in the right way. So there's no disruption happen. So the telegram integrity is there. It's intact and the data is fine. And we'll talk about this in the advanced course in details, by the way. Then you have the data blocks port where you have all your information that you need. So the data blocks mostly contain the actual useful information. Okay, and we'll talk about this like switching or dimming. And this also talks about the start and the end of the ready telegrams. So this is a data block. So analyzing a data block, as you can see, there is a control field in here, then individual address, then destination address, then control field, then data, then checksum. Okay. This information causes data to be transferred, such as commands, messages. This is the useful information part in here. Okay. It also appears the individual address. Individual address is the address of the sender, the device, like a button or something. This is the individual address. Then destination address. In RF, I have two types of destination address. It's either individual address, okay, and individual address, by the way, is the one that we talked about, like the line and area dot line dot device, like 5.5.6, something like that. Okay, but destination address in here it can be individual address or a domain address. So if I'm talking about KNX E devices, RFE devices, easy devices, then mostly it's an individual address because devices are connected together. If I'm talking about more complicated projects, like a secure mode, the S mode, then I have here a domain address, okay? A domain address is something to identify that those devices are working together. Here is the medium, the radio, there is the PCU and the AM application module. In the RF components, most of the time, the PCU part and the application module part are single device. And if it is an S mode device, okay, then it will be loaded using the ETS. If it is an E mode device, most of the time the devices are coming with the application module installed in them. Also, there's some definition here, the unidirectional and the bidirectional. Unidirectional devices will only send or receive. This is a unidirectional device. Uni here for uni, like one direction. Bidirectional device who can send or receive at the same time. Repeating, because the signal, we said that the signal might have some attenuation, then I can use some kind of repeaters. Repeaters here are devices that are connected via the line. So they are main devices. powered not by battery, but powered by line itself, like actuators. And I can have up to 2 repeaters in the KNX domain I have. So in RF repeaters, I can have up to 2 repeaters. On the line segment, we said we can have up to 3 repeaters. In here, I have up to 2 repeaters only. And then they can take the signal like here, okay, and then propagate it to other devices as well. So this guy gives the signal to this guy, and this guy took the signal and put it to the other devices as well. Okay. The topology in here is very simple. I can have a project that's completely made by RF, pure RF network. In this case, I have devices like actuators, mostly in the box itself, flush mount, or sensors or devices, okay? Completely purely RF, or I have a combination that I have a network or a project with part made by twisted pair and the other part is connected by RF. In this way, I connect the two domains together, like the KNX installation using TP with the KNX installation using RF using a media coupler. Okay, like we said before, we have a line coupler or a media coupler. Line coupler connect two lines together. Okay, IP router will connect the IP network with TP network. In here, I have a media coupler, which is the normal situation or the normal device. In this case, it will be a TP to RF media coupler. So it's taking, from one side, it's taking TP, a cable is connected. The other side, there is an antenna to connect to the other device. Okay, so this is a media coupler. In this case, it's a media coupler to RF. And most of the time, this is when I'm using the RF. So normally, I don't use RF as a pure installation, because if I'm using only wireless installation, I can go to, let's say, ZigBee or Z-Wave. But most of the time, I have an installation of KNX with the twisted pair, and then I need to add a part that is where I cannot put cables. In this way, I can add the RF part of the devices as well in my project. In case of E-mode devices, as we said before, you can link the E-mode devices together with mostly something like that. So you bring the sensor and the actuator, you press on this device, let's say a few times, and this device a few times, then they go into pairing mode, and then they're connected together, and that's it. If it is S-mode device, then you are using the ETS program to connect them together. Then how to connect the RS in case I have pure RF transmission, how I can connect my laptop or my PC to these RF devices, because there is no cable in here. In this way, I can use an RF key like that. Okay, where I can connect then the ETS on my laptop or on my PC to the RF network itself. We're done with this. It's a small chapter. Normally in the exam, it comes with only 5 questions come in the exam, and mostly they talk about the frequency, about why I'm using multi-channels, or the number of repeaters, and when should I use RF or something like that. Okay, see you in the next chapter. Take care. Assalamu alaikum.